Our first task in addressing the question, the problem of the tangent line, is to get a handle on infinity. This is, again, very rough and very crude and very unofficially stated, but we need to get just get a feel, to get a handle on how we're going to work with, how we're going to deal with the notion of infinity. What does it mean? How do we work with it? What are the ramifications of that? So there's the ideas of infinity. It turns out that any time in mathematics you're dealing with the notion of infinity, the tool, mathematically, we use to handle infinity, whether it's the infinitely large or, more for our instance, the infinitely small, anytime we're dealing with any notion having to do with infinity of any kind, the tool we use is a limit. And so that's what I'm going to introduce here, is what is the basic idea, what is the thought process of a limit. Then we're going to talk about the much more official and precise definition of a limit, how to sort of get used to walking around that room a little bit. And then once we get used to where the furniture sits, then we're going to be able to do some specific computations and be able to work with infinity to make it find the ideas and the quantities that we're looking for our work in the calculus. So, what I want you to do is to think back way back to the very first time you were just a little baby algebra student and you were graphing the function y is equal to f of x. Now, depending upon whom you had as an instructor, they probably did a very similar thing to this. You plotted a bunch. Remember, way back when, before you even knew what a parabola was, this was, ooh, this is unfamiliar. I don't know what you're talking about. It's y equals x squared. You had no idea what was going on. What you did was, you plotted, you got an x, you got a y, you got some numbers, you got some ordered pairs, and you plotted a collection of points, 1, 1, and 2, 4, and 3, 9. And depending on whom you had for an instructor and how persnickety they were, you would also plot in either some fractions or some decimals, and you plotted in more and more and more of those points, and you saw more and more and more of a pattern. And then at some point, the plotting stopped, and what you did was you played connect the dots. You drew a nice smooth little curve to make your little parabola. And it turns out that's correct. But at the time, and you didn't realize this, you were making a whole boatload of assumptions when you drew this nice smooth curve. Among other things, it was correct, but it turns out you were assuming, for example, that it was a curve rather than, for all you knew at the time, again, it turns out not to be the case, but it might have been a collection of straight lines. You didn't know that at the time, but you were probably told, and correctly so, that it was not a collection of straight lines. It is a curve. And you assumed at the time it was a smooth, connected curve. It turns out you assumed there are no holes anywhere. It turns out that's correct. But at the time you didn't know that. That was an assumption you made. What we're going to do is take a little bit closer look at that. Because yes, y equals x squared is one of the simplest functions around. And it does have this nice, neat, convenient, pleasant, familiar behavior. There exist other functions that don't have this good behavior. They're much less well behaved. And they might have issues arising. And if that occurs, the question is, how do you handle that? What we're going to do is learn how to handle the ones that behave nicely first, develop some skill, develop some techniques for how to handle the curves that behave nicely, and then be able to transfer those skills. What happens if the curve doesn't behave quite so nicely as these very basic ordinary ones? And that's what we're going to be on about. And so, one thing I want to look at is this. Consider my yardstick I have here. Now, from your perspective, looking from that distance, the distance between my yardstick and the camera is about 2 feet. It looks like a straight line. And if I were to use this to draw Let's see something. We understand that is supposed to indicate that there's a straight line there. But you, even at this resolution, you can probably see this is not a perfectly straight line. This is not a perfectly straight yardstick. In fact, it's not very hard to see here. Even at the scale that you can see, if I zoom this in, you can see that between an 11 and 12, you see there's a little imperfection there. All right? And I think there's one up here between 15 and 16. See, between 15 and 16, there's a little imperfection. Do you see it? So it's not, we understand, this is not a perfectly straight line. Now, from this distance, it does look straight. Closer up, it doesn't. And we understand that if you were to zoom in on much finer scale, you would see irregularities in the wood. And if you zoomed at a much closer scale, you would see irregularity in the atomic structure. The same kind of thing happens. Imagine if I have a salt crystal and chop off the salt crystal. It looks like a flat surface, a flat plane. But if you look in closely, you see that it actually is irregularly shaped. And if you look closer, you begin to see the structure of smaller salt crystals that make up that larger plane. And then if you look at sufficiently close, we understand you actually see the atomic structure, the crystalline structure of the sodium and the chlorine atoms. So whether or not something appears to be smooth and straight could depend on the scale that we look at it. Now, in mathematics, even though we represent this with a physical line, there actually is physical chalk atoms on the physical blackboard atoms. We understand there actually is a physical object here. But ideally, we say, is this a perfectly smooth, perfectly thin, perfectly straight line? In the idealized, or the official word is platonic, but in the idealized view, do we understand this to be a perfectly straight line? Well, the question is this. When you drew, the very first time you drew your little smooth curve, you were making an assumption. Because just like this appears to be a nice smooth curve, we understand that, if nothing else, at the atomic level, the atoms of the chalk do not actually physically touch each other. There is a gap between. And for all we know, it could be that there is a gap between them at higher levels of magnification. So the idea is this: if I take just this little piece and magnify that and look at just that piece of my picture, then what I have is a curve that comes through like this. And then I take that little piece and magnify it. And then there's my curve. And then take that little piece. The question is this: depending upon how extremely we magnify this, and I'll give you might need to magnify it hundreds of quadrillions of times. But potentially, it could happen that if you magnify it close enough, it is no longer a connected smooth curve. Actually, what you have here is an irregular collection of individual points. That is potentially a possibility, that it only appears to be a smooth connected curve. But if we magnify sufficiently, the question is there a scale at which this loses its integrity? Well, you might have to get very, very close. But of course, if we're talking about infinity, you can get as close as you like. So that's the idea we're talking about here. Is there a scale of magnification that if we got sufficiently small, that this might be happening? What we want to do, one of our first tasks, is to verify that for the ordinary kinds of functions you've been dealing with up until now. X squared, cosine of x, natural log of x. All the basic kinds of functions you've dealt with so far. What we need to do is verify that this is not what happens. Because if this occurs, it turns out, if this occurs at some level of magnification, at some finite level of magnification, if this occurs, then the tools of the calculus don't work. In order to make sure that the work we do is valid and mathematically rigorous, we need to ensure that this never happens. The tool we use to ensure this never happens is the idea of a limit. And so our next discussion, our next video talks about how do we get from this basic general idea to something much more rigid, much more official mathematically. And so that's what we're going to be on about in the next video.